Welcome to the tutorial over 8.3 graphing reciprocal functions. Your new vocabulary is going to be reciprocal functions and hyperbola. Alright, so our key concept for this video, we're going to be talking about rational functions, but they're now going to be called hyperbolas because we are going to make them a little bit more complicated than what we're a little used to. Okay, so the parent function is going to be 1 over x. You need to know that because we're going to be dealing with transformations in this video. It's going to be called a hyperbola. It is not hyperbola, it's hyperbola. And then the domain and range is going to be all non-zero real numbers, except x cannot equal 0 and y cannot equal 0. We have the asymptotes, which means that you cannot actually cross those. X equals 0 and f of x equals 0, or you can say y equals 0. There are no intercepts, and x is not defined. Alright, so example 1, we have limitations on domain. It says determine the values of x for which f of x is equal to 2 over x squared plus 5x minus 24 is not defined. Alright, so anytime we have rational functions or hyperbolas, the denominator cannot be 0. So anytime you need to know whether or not it's not going to be defined, you're going to set the denominator equal to 0 and solve for x. Alright, so the factors of this, we're going to look at 24, and the factors of 24 are 1 and 24, 2 and 12, 3 and 8, and we have 4 and 6. What you want to look for is which one of those are going to give me a 5 if I add or subtract them. And it looks like 3 and 8 are going to do the trick. So we have x and x, 3 and 8. Now, this middle sign goes with your bigger factor, so we need a negative to go on the 8, and we need to multiply to get a negative, so this needs to be a positive, because a positive times a negative is a negative. Alright, so from here, we need to set each factor equal to 0. So, I have x plus 3 equals 0, x minus 8 equals 0, minus 3 on both sides, so I get x equals to negative 3, and x equals positive 8. So my answer would be the function is undefined for x equals negative 8 and x equals 3. Alright, example 2a, we're going to identify the asymptotes, domain, and range of the function. Alright, so it's a little hard to tell on this picture, but we have our function, which is f of x is equal to 3 over x minus 2. And the asymptotes are where your function do not actually cross. They get really, really close, but don't actually cross. So if we look horizontally here, it's not actually going to cross the x-axis, which that is called f of x equals 0. Okay. And also, we know that the denominator can't equal 0, so if we have x minus 2 equals 0, x cannot equal 2, because that would make our function negative, or divide by 0, which is undefined. So that means we have an asymptote at x equals 2. Okay, so my two asymptotes are x equals 2 and f of x equals 0. And it says state the domain and range of the function, which it hits every single x value except for x equals 2. So you would say the domain is all real numbers except x cannot equal 2, and the range is all real numbers except f of x cannot equal 0. And that would be your complete answer. Example 2b, we're going to do the same thing, identify the asymptotes, domain, and range of the function. Okay, so we're going to look here, and we see our function is 1 over x plus 2 plus 1. So the first thing we're going to do is set this denominator equal to 0. So we have x plus 2 equals 0, so x cannot equal negative 2, which is this vertical asymptote here. And you can kind of see that on your graph. And then we need to figure out what our horizontal asymptote is. So we're actually going to take our function and set it equal. Actually, let's think about it in the transformations. Okay, so we know that our parent function is 1 over x. So this plus 1 means I took this and I raised it up 1 unit. So the horizontal asymptote is usually at x equals 0. F of x equals 0. So if we raise the function up 1, that means we raise the asymptote up 1 as well. Okay, so we're going to have an asymptote of f of x equals 1. Alright, so this actually gives us our asymptotes, and our answer will be we have asymptotes at x equals negative 2 and f of x equals 1. And so our domain will be all real numbers except x cannot equal negative 2, and our range is all real numbers except f of x cannot equal 1. Alright, so now let's talk about transformations on reciprocal functions. Okay, so here's our general formula here. I want to write that down. We have a over x minus h plus k. So the horizontal translation, think of it as backwards rolled again. If h is positive, meaning it's positive, but we have our minus sign in front, it's actually going to move to the right. Okay, so if this says x minus h, that moves right. If it's x plus h, that moves left. The k tells you whether or not you move up or down. So if it's a positive k, it moves up. If it's a negative k, it moves down. And then a, we'll talk about the orientation and the shape. If a is less than 0, the graph is reflected across the x-axis. If the absolute value of a is greater than 1, the graph is stretched vertically. So for instance, like 2, 5, 100. If the absolute value of a is between 0 and 1, so like a fraction, so like 1/2, 1/8, etc., it means that the graph is compressed vertically. Alright, so it says graph the function f of x is equal to negative 1 over x plus 1 plus 3, and state the domain and range. So the first part's pretty easy. You can actually graph this on your calculator, which here's the picture of it right here. Now, the next thing we need to do is figure out why we have x cannot equal negative 1 and f of x cannot equal 3. Okay, so first we're going to take the denominator and set it equal to 0. So x plus 1 equals 0. We know that x cannot equal negative 1, so that's where this piece of our domain comes in. So we know that the domain is all x values such that x cannot equal negative 1. And then for our range, we see this plus 3 here. We know that our horizontal asymptote is usually at f of x equals 0. However, that 3 means we're going to raise it 3 units, so 1, 2, 3. So that now means that our horizontal asymptote is at f of x equals 3. So that's how we actually get our range. So f of x is all real numbers except x cannot equal 3. Sorry, f of x cannot equal 3. Alright, so example B is the exact same thing. We're going to graph the function and state the domain and range. Okay, so again, you can actually graph this on your graphing calculator exactly the way you see it, and you should get the following graph. If you need to find specific points, you can always go to the table function, and you can get specific points in order to graph it correctly. Okay, Alright, here we have to actually find out what x cannot equal, and I know that we have our answer here, but I want to show you how you actually get it. We have to set this denominator equal to 0, so x minus 2 equals 0. So if we add 2 to both sides, we get x equals 2. That means x cannot equal 2 because it would make the denominator 0. Okay, so that's where this comes in for our domain. And we can see that here on our graph. Always make sure when you're graphing these, you show your asymptotes by dotted lines. Next thing we need to do is we need to look at our transformations, whether or not our graph moved up or down. The way we check that is we have our -1 here, so it means we went down 1 unit. We know that our regular horizontal asymptote is at f of x equals 0. So that means if our graph was shifted down 1, that means our asymptote is now at f of x equals 1. -1. So that's where on our range, f of x cannot equal -1. Example 4, we have a computer train that is a non-stop service from one city to another, a distance of about 25 miles. Write an equation to represent the travel time between these two cities as a function of rail speed, then graph the equation. Alright, anytime you're talking about distance, rate, and time, you're going to use the formula distance is equal to rate times time. Okay, so that stands for distance equals rate times time, and I wrote it out for you. Alright, so what we actually want is it in terms of t. Okay, so we're going to divide both sides by r, and we get t is equal to distance divided by rate. And the next thing we want to do is actually plug in what we know. And we do have a distance of 25 miles, so we're going to replace d with 25 miles to give me t is equal to 25 divided by r. So now that we actually have our function, we need to plug this into our calculator. And on our x and y axis, this is going to be r, and this is going to be t. So you can think of r as your x value as you're plugging this in, and you can think of t as your y value. So when you're plugging this into your calculator, you can say this is y is equal to 25 divided by x. So once you plug that in, you should get the following graph. Alright, example 4b. A computer train has a nonstop service from one city to another, a distance of about 25 miles. Explain any limitations to the range and domain of this situation. So let's think about it this way. We're talking about a train, and we're talking about time. And is time ever negative? And the answer will be no. Time is not negative. So we want everything to be in the positive first quadrant. Okay? So that's the first thing. We want everything to be in the positive first quadrant. So the domain and range are all limited to all real numbers greater than 0 because negative values do not make sense. And there will be further restrictions to the domain because the train has a minimum and maximum speeds at which it can travel. And thanks for watching this tutorial.